So now that we have this picture in our minds of how a sound wave may travel, we want to see if we can apply a wave model equation to describe the behavior of a traveling sound wave. And so we can see here just a picture of some air fluid where it's highlighted the points where the air fluid is under compression and expansion, similar to that long spring or slinky. This is like a model to keep in mind. So this sound wave is traveling to the right, perhaps from a speaker source on the left side. And we can see the wavelength is lambda between the positions of the points of compression. And so that we can imagine that if you think about a particular fluid element inside of the air, so pick one of those like red molecules in the simulation earlier, you can see if we can describe its position as a function along this sort of length x of this tube of air, and as a function of time as it oscillates back and forth as this sound wave travels. And so similar to traveling transverse waves, like waves on a string, here we can describe the position S of the oscillating fluid element as a function of the position x along the medium in which it travels and the time t. And so similar to before, we can consider an amplitude. So here we'll use the same notation as the picture here for the maximum position Sm, but that's the same as the amplitude A, times some harmonic function. So it turns out we can model the oscillation of the fluid element similar to the same idea as we looked at the transverse waves. That comes from the model of waves and simple harmonic motion. And so similarly, we have, if I have a constant wavelength, and we have a wave number k, and a frequency f gives us a frequency omega of the wave. And then we could have a phase phi in general, so we've left that out here. But you can also imagine that you could describe not just the position of the wave, but also the changes in pressure of this fluid element. And so you could also describe the change in pressure as a function of along the position of this, let's say, tube, x and t of time. And that requires us to know some amplitude of pressure, so we'll call it the maximum difference in pressure. And this would be similarly a harmonic function. Here we'll write by convention the cosine and sine for the displacement and pressure waves respectively. And here we'll explain why we do that through sort of a summary. In this picture we can see that as the speaker vibrates, the fluid of air begins to oscillate back and forth. And on the left picture in the red graph, you can see that the change in pressure initially is 0. So that is saying that the part right next to the speaker has no change in pressure. So that's sort of the same as what the pressure is outside. So that could be considered the same as the pressure in the atmosphere. Right? So atmospheric pressure. So therefore there's no difference in pressure with the air surrounding it. Whereas where the amplitude is, the change in pressure is maximum with respect to the outside air. And so that's where you have the highest compression and therefore highest change in pressure. And when you have the lowest compression, sort of if you have the most expansion rather, then you can also have negative changes of pressure with respect to the atmospheric pressure, which is sort of the equilibrium pressure here. And similarly on the blue graph, you can see for the same traveling sound wave, you can write its position of these air molecules or fluid elements of the air as they oscillate back and forth, S, as a function of its position X along the tube. So these are all, both graphs are snapshots in time of the sound wave. And similarly, for the displacement, you have we see here, we start with at time equals 0 at an amplitude that's maximum, and it's positive, so that's sort of similar to simple harmonic motion. Or like a spring, you've pushed it out of its equilibrium, where the equilibrium is in the S equals 0 position here, and then it starts to oscillate back and forth and go to through equilibrium and back to negative amplitude as it tries to restore backwards, and this continues as the wave travels. So we'll look at some of these properties, but you can start to see that these in general can also include a phase phi, and we will start to be able to solve traveling sound wave equations.